Um, I think I first mentioned about artificial intelligence and machine learning at the 2018 NDA convention, Austin. The response was kind of lackluster, if it was not jaw-dropping, and I can understand those concerns, right? As human beings, we are, am I good? Okay. As human beings, we are, very averse, and there is an inherent inertia to change, right? But if you know, change is the only thing that is constant in life, right? So the folks that are promoting our into these endeavors of bringing change, they are not deterred by this. But it is the rest of the other crowd that always has kind of those notions or those skepticism, and eventually we overcome, right? That's not the first time that we've been scared by folks about artificial intelligence. Remember in 2000s, we had the Y2K problem, right? The doomsday, but we survived it, right? So we will. What I'm gonna do today is kind of, as you can see on the graphic, on the left one, this graphic is again generated by ChatGPT, right? So I've included a few graphics in here to kind of also showcase some of the pros as well as cons of artificial intelligence. It's a good graphic to start with, but you'll also see that the theme keeps on repeating, right? But the kind of idea or the central point about my talk today is, how are we going to integrate artificial intelligence and machine learning? It is inevitable, but how are we going to integrate it purely for the demolition industry and as well as the construction? Because I consider demo or a deconstruction industry to be part of the AEC, that is the architecture, engineering, and construction industry, right? So we will look at how can we integrate it for effective demolition planning. We'll also look at how we can manage risks and mitigate, manage safety and mitigate risk, both on the financial side as well as the operational side. But in addition to that, the biggest thing that here is, because that's also the theme of this convention, is how we're gonna use AI to promote sustainability. That's the agenda. Again, no pun intended, or I do not want to offend anyone, but the agenda is more than a wrecking ball. It's an AI-powered wrecking ball. That's how I would theme it, right? So within this agenda today, we look at how we're going to integrate AI to effectively come up with demolition planning, how we're going to also address risk management, financial, operational, how we're going to use AI to promote sustainability. And at the end of it, I'll talk about a technology that we are developing in-house that kind of addresses the about 3 points, right? In a way, not all, but it touches upon all of those 3 points. It's a technology that we are developing for effective, for accurate estimation of scrap as well as commodities. Okay, what is AI? So what you see this image here to the left, that is generated again by ChatGPT. I gave it a simple task, hey, generate me an AI-powered demolition, right? What you can see is, yeah, this is possibly coming. You may have humanoids performing some of the demolition tasks that are high-risk profile tasks. Why not, right? If we can. So AI and machine learning is not going to take away our jobs. We're going to adapt, right? We're going to adapt our skill sets. So this is coming. Now, just to give a little bit perspective of what is AI, right? In essence, you're basically teaching computers to reason, to learn, and to act like human beings, right? And I think I have a couple of things to say. One is, do not get deterred or scared about the technology, right? This technology, like especially the technology world, wants to make everything fascinating, but in doing so, they also scare the larger crowd, right? So if I were to say, I would say this: do not let anyone, Elon Musk, their way into scaring you about AI technology. AI is simple. It's simple way of putting together in simpler form of mathematics, but you are layering them in a complex way. But these are very simple ways of I'll touch upon it. These are what we're calling as neural networks, wherein we are trying to mimic human brain by using simple linear algebra. So if you studied, even in high school, you studied linear algebra, right? And with those algebra, you're trying to activate a neuron, which is an artificial neuron, like in a human brain, to function like a human brain, where those neurons are basically triggering some activation functions, right? You give it some data, and that triggers some activation functions, like what happens in a brain, and that process churns or starts the process of learning. And once you train a model or you train that brain, then you can put it or deploy it to do tasks that you have trained it for, right? So it's simple mathematics layered in complex layers to solve certain problems, right? Yeah, some of the solvers that we use to train these AI models, they are mathematically, computationally as well as mathematically very complicated, but the overall framework is simple mathematics layered into complex framework. Now, the algorithms that we develop, any kind of AI algorithms, they need to learn, so they need data. The more data you give them, the more generalistic they become, right? So I'll touch upon an example as to why we need more data and why they are data hungry and how more data only makes them more robust, right? Then other thing about AI is there's no bad day for a computer unless there's power outage or anything. If I train that damn model to do a specific task, it will keep doing that. Imagine you go to a doctor, right? And there's algorithms that have proved that AI models are better detecting skin cancer than even physicians. On any given day, if the physician is having a bad day, he may perform bad at work. The computer is not going to do that. There's no bad day for the computer because it's been trained to do a specific task, and it will keep on doing that with the accuracy at which it is trained for. Let me explain this using a simple task, an AI task, right? This AI task, and this is a simple task when everyone starts learning about AI, is these are the simplest tasks that you learn the theory as well as the implementation of AI. Here then, the task is to identify a cat. So if you are providing this AI models pictures of any animals to pretty much anything that exists in the nature, right? If you provide a picture of it, it should be able to tell if there's a cat in that picture, right? So this one is what is called as a supervised learning because I'm telling it, I'm training it to only identify a cat, right? So the way it works is, what we call here is we create an AI model, which is like an artificial brain. And again, as I explained, it is a way of mimicking how neurons activate in our brain through constructing artificial neurons, layering them up, right? So that is what we first thing we do is we build an artificial neural network, right? These are called neural networks, and there are various forms of neural networks. There are convolutional neural networks, recurrent neural networks. Let's not go into details of that. But if anybody is interested, we can nerd out during coffee breaks, lunch breaks, or even during the dinner tonight, right? But imagine now, you create an artificial brain that can work like a human brain using simple mathematics layered in complex layers, right? Now, what you do is, then you need data. You need to tell the model what a cat looks like. So I'm going to generate, there are databases right now, open source databases, that are billions and billions of pictures of cats. So basically, you tell the model, you pick all the photographs of that, and you say, this is a cat. And those cats could be all kind of breeds of cats. The cat could also have a skewed cat. Its face is something, a cat that got hit by a car. But the AI model should be still able to identify that cat, that this is a cat that's face has been mangled by a car, right? So you kind of provide any and every form, kind of picture that you give of a cat because you want it to be as robust as possible. And you start training that AI model. Now, what that model inherently is looking at is, and this is a computer vision algorithm, right? Wherein you are using the same algorithms for self-driving cars, wherein you have LiDAR scanners, you have cameras put on the car, and as the car is driving, you are getting pictures at certain frame rates, and it is going through each of those frame rates, the computer vision models in the self-driving car identify whether it's a human being crossing the street, whether it's a traffic light, whether it's a car, right? And so that's exactly what this is doing. So you make the model so robust that it can identify a cat. The way it is trained is, you convert the picture into a grayscale, right? And then a cat has a certain geometric features to it that makes it looks like a cat. Its eyes, its face, its whiskers, and there is way these geometric features are layered. So when we say this simple maths that you're putting in complex layers, these complex layers are learning those geometric features of the cat as to how a cat looks like, right? And that's why we want to give it all kind of pictures of a cat, right? And then this is a kind of a trial and error method. You don't train it in one shot. It's not going to happen. How many layers of those simple maths I need to layer? We call them as hidden layers, a technical term in convolutional neural networks. So it's a back and forth. Then there's something called as reinforcement learning. If I train a model to identify cars, I can train that model, then I can use it to retrain it to learn dogs or any other animals, because it's called reinforcement learning. Now that model has learned to identify geometric features, right? I can take that, so it is, and use that and train it to teach how a dog looks like, right? And there the effort would be 50% than building a brain from the scratch and making it to train look like a dog, right? So you give it as many pictures as possible, and it starts learning. And it's an iterative process. At every iteration, you are looking at the accuracy. Because what do you imagine for a use case here, I have 500 pictures of cats. I use 400 pictures to train it. And the rest 100 pictures is never seen. So I feed the next 100 pictures, and out of 100 pictures, maybe there are 90 cats, the rest are something else. Does it identify all the 90 cats? That is how I'm looking at its accuracy and performance, right? If not, again, I'll tweak the model. So it's an iterative process, and I keep doing this. That's what is called as training until I reach a satisfactory level of accuracy. Now, that level of accuracy depends on where you are deploying this model, right? Imagine if this is a self-driving car, I want that model to be as accurate as possible. I don't want to go and hit a human being when I'm driving, right? So those applications decide what is the level of accuracy I'm looking for, and that depends on what is the hierarchy or what is the architecture of model, what is the computational resources I'm requiring to run those models. That is why we have all of these data centers, the front-end data centers that in real time will basically are running all of these models, right? So once you train it and once you're satisfied with that accuracy, the next thing is called as inferencing. Where is the actual deployment? And so I use those 100 pictures to kind of verify it, and it's done. Now the model is done. Now I can give that model to any one of you, put it on a picture, put it on a computer, and then you have this open source database, give it any number of pictures, and you should be able to identify where is the cat. The cat could be skewed, the cat could be hidden somewhere, right? It will mask, but it will identify. So that is pretty much the process of how do you do AI, but this is purely like computer vision, right? So let's look at the various types of AI models. I'll quickly go through each one of these with some specific examples, right? Let's start from let me orient myself, from the right. Machine learning, right? So these are purely more like data. So you feed them data, they learn interdependencies of data. Like to give an example, if I were to feed it data for Apple stock over a period of 25 years or 30 years, or any time Apple went public, right? It keeps on looking at not only that data, but I'll provide it the world data about other in the same sectors, other competition, how it's providing, anything that will basically influence Apple stock. I'm going to provide it all of that data over the last 25 years. And that is what we call, those parameters is what we call as a feature space in AI. So it is learning all of those interdependencies between these parameters that is dictating AI, Apple stock. And once it learns that, then you deploy it, it will predict what the stock is going to look like over the next 5 years, 2 years, 3 years. And that depends on how well the parameters you have picked up, right? If I pick 25 parameters, and each parameter is not going to have the same weightage. Some parameters, like if I'm looking at the technology space, that parameter have more weightage than looking at other, which will have less influence on Apple stock, right? So it'll learn all those interdependencies. But I should have that common knowledge as to what is that data that I need to provide it to be able to learn. So that is machine learning models. You could do the same for real estate. The next is deep learning models. It is like wherein it is huge amounts of data, and it's unstructured data. There's no correlation in it. Like if a language, right? If you have tons of books that needs to be read, or audios, right? Signals, anything, tons of data, there's no structure to it. Those are like deep learning models wherein then you're layering these simple maths into layers and training them to identify. That's called deep learning. So most of what you see in today's high-end applications, it's all deep learning. Then you have generative models wherein, as I said, generative models are usually employed wherein you want to generate more data. If there is no data available, engineers and scientists generate artificial data, right? And that artificial data almost looks like a cat, but it is artificially generated. But now, and those algorithms can introduce the level of robustness or the generality in the shape of a cat. The same breed of a cat, if I bring 10 cats of the same breed, they'll all look different. So these kind of generative models can generate for a same breed different cat models, right? It can also take some existing old movie from the, like, black and white movie, you can add color, so that's also one way of enhancing data. So that's the purpose of generating models. Hybrid models is kind of a mix of all of these models, not touch about it. Natural language processing models, like you have ChatGPT, right? We'll tell it something. It processes all of the database that is there. It has learned to answer questions by learning about the world. And we trained it to learn about the world, right? We told it 2 + 2 is 4. So if you ask it, it's going to say 2 + 2 is 4. It's not going to say 2 + 2 is 5 because we have trained it, right? So, but these models are the ones that can process text requests, speech requests, and answer you. So any kind of chatbots use natural language processing. Computer vision models is a subset of deep learning models that are used for purely analyzing visual data. Anywhere, if you're using drones to do some scanning, identify for security reasons, or even self-driving cars, to pretty much anything, like you use them for facade inspections, right? Now let's switch into how we talked about AI, we talked about how simple it is. Let's not get scared about AI and how we can effectively adopt AI, right? Now let's see how we can effectively adopt AI for demolition planning. So this is, again, I asked ChatGPT, generate an image that basically mimics or showcases or illustrates AI-powered demolition. I don't think so I necessarily agree with this, but so that's what some of the pros and cons of this ChatGPT, because a ChatGPT is a very generalistic AI model, right? It is supposed to solve the problems of the world. It is not tasked to serve specific problems. So that's why it doesn't do sometimes a good job of doing what it's asked to. AI-powered demolition planning. So some of the stuff that we are doing already is reality capture and integrating that into your building information management systems, right? Where we use drone photogrammetry, we use LiDAR scans, create point cloud models of this, where you photogrammetry captures all the exterior topology, LiDAR scans captures all the interior, you integrate all of this, you have an entire digital asset, right? Then you bring that into point cloud models, and then we have frameworks that can move from point cloud models into BIM modeling, then we can use for demolition planning and sequencing. There is already AI-powered structural engineering design that's happening. What we are doing is, there are design standards and codes. These are all rule-based principles, right? We feed that. And if I have been designing, like my company designs, we are known for designing high-rise buildings. So I'll provide designs of last 25 buildings. The standards are the standards. The building code is the building code, right? But now it understands the design intent of each of those buildings, 25 buildings, the architecture's intent, the structural intent, where is the locale, whether this building is designed for seismic activity or a wind loading. Depends, right? If you're on the West Coast, the governing for lateral load case is gonna be seismic. If you're in Florida, it's gonna be wind, right? So it understands all of that, and then it starts optimizing the design. So we are not doing it to totally we'll eventually get there, but right now we are trying to look at what's the low-hanging fruit where we can effectively utilize. So AI-powered structural engineering is already happening. We use it for coming up with member sizes, for column sizes, beam sizes, reinforcement layout that basically gives me the most optimum layout, because it is learned from all the 25 previous designs that I've done. Right now, if I were to bring a new engineering intern or a new engineer, rather than him having to go through all of this, that work can be done by this AI-powered structural engineering, right? AI-powered demolition engineering. Again, we have started integrating reality capture. Again, this is absolutely a possibility. There's nothing, if you can do structural engineering, why can't you do demolition, which is the reverse process of building something, right? So if you were to give it last 10, 15 plans of power plants that you've done, it can understand what is the capacity, what is the structural system, where was this power plant located. Based on that, it can understand whether the governing load case for a lateral, is it wind or is it seismic? It can understand soil, because you'll provide all of the geotech information. Based on that, it will tell you possibly what is the most optimum way of deconstructing this power plant, one that helps you manage safety and mitigate risk. At the same time, it is cost effective. But I need all of that data. So that's why I keep on saying they are data hungry. The more data, the more generalistic, more robust they become. So I'm going to showcase a project here where we have integrated not AI, but per se, the initial part of it, a reality capture. We have possibly in the crowd Brian Bauman and Nick Philippi from B&B Wrecking. So we are contracted with them. This is possibly the most complex power plant project we'll ever do. The complexity is because of, if you were to take this power plant and put it somewhere else, it would have not been the same complex, right? So sometimes the topology or where the structure is located sometimes makes it complicated. The complications here, as you can see, on the right, bottom right, is Ohio River. This is near Stratton, Ohio. On to the left, past the turbine halls, it's all hills. So you have this narrow strip of land, right? And you are only bound by this land. The first 4 boilers were built in 1962s and the turbine hall, right? And in 1967, they added boiler 5, 6, 7 further to the left or towards the bottom of the screen. And as EPA regulations started kicking in, they need to add more. Where are they going to do it? Either add over the existing structures or snuck them between existing structures. Like you look at the SCR in 1968, they snuck it between the smokestack and the boilers 5, 6, 7, right? And then between the 2 smaller boilers that you have and the boiler house 1, 2, and 4, they had the original old boiler houses. Then in 1980, when the baghouse technology and the electrostatic precipitator technology changed, they put 4 baghouses to cater for the 4 boiler houses to the total right of the screen, and then 6 precipitators to cater for boiler houses 5, 6, and 7 over the highway. They basically built a bridge and put those 4 boiler houses and 6 precipitators over an active highway. And then in early 2000s, you had to install flue gas desulfurization units, what we call as the scrubbers or the FGDs. Now, all of the flue gas, first from the boilers, it goes into the SCRs, and then into the baghouses or the electrostatic precipitators, and then it goes to the FGD. You look at all of the ductwork that is there, and to the left, what we call it as the Great Wall. That's like a 200-feet wall of ducts coming from all the 4 precipitators and the baghouses that goes into those 2 FGDs and then into the FGD stack. That was put in 2005. So this entire plant was built over a period of 40+ years. So we spent almost like 6 engineers, 3 months on this project only to gather the data, to understand what structure is relying on what in terms of lateral stability, in terms of gravity loads, identifying where we make these separations, which we can do a top-down mechanical demo, which we can do an explosive felling, which we need to do a crane pick, right? So the significant part of this project was to have the buy-in of Ohio Department of Transportation because of the risk that was involved of taking down those 4 baghouses and 6 precipitators over an active highway. right? So what we needed to do was come up with conceptualized plans. These are not like graphical illustrations, but an engineering thought process went into it. We studied the structural system. Based on that, we started how we're going to take it down, right? We're going to close one of the lanes, and other lane, we're going to make it a two-way, and on one of the lanes, we are going to basically come up with two big cranes. Back then, we had decided about going with a 1,800-ton crane. If Nick is here or Brian is here, they'll give you all the configuration of all the cranes that we are using on this job. This job is very, very crane heavy in terms of deconstruction, right? And we needed to kind of put forth these plans to Ohio Department of Transportation to have their buy-in. Because on this job, you drop a piece of steel on the active highway, that's the end of your project. That's how risky it was. So what we did was, we kind of did a drone photogrammetry, got the entire topology. Back then we didn't have the resources to do an entire LiDAR scan, but we had all the interior structural drawings. So we built a CAD model, and then we merged the exterior topology from the drone photogrammetry with the CAD model. So now we had an entire digital asset. You could slice and dice it. If you take a point cloud model, if you slice it, there's nothing inside, it's hollow. Here, everything is built in, right? And then we started, and it's all 1:1, and we produced this graphical illustration of how this deconstruction activity is going to go on to have the buy-in for them. You want to say, go ahead, we can take a look at this project. So the next slide is basically going to show all of this deconstruction sequence. So this is a drone photogrammetry, and then we have integrated the BIM model into it. So you can see that's an active highway. You can see the 4 bag houses and the 6 precipes. That's what is highlighted, because that's what we needed to show to the Ohio Department of Transportation. So some of those bag houses, as well as precipes, we are doing 3 picks. Basically, some of these picks are upwards of 400,000 pounds. Yeah, huge picks. Yeah, there are a couple of other presentations where you can see some of the ductworks. Those are like 40 to 60 feet tall, and yeah, people standing in front of them like 5 to 6 feet. Yeah, the order of magnitude of the geometry, yeah, kind of scares you. So that is where again, we are a long way to go. This is when we started the job towards the end of 2023. So we have come a long way after that in terms of advancing this technology. So kind of touch upon, again, some of this is going to be more of philosophical. I can get into the technical details, but given the time constraints as well as this one, I wanted to kind of touch upon everything that addresses those 3 aspects of integrating AI. Let's look at AI-powered risk management. It's already there in the construction industry. Construction industry has already adopted it. There are software that do a lot of AI-based risk management that are integrated into regular workflows. You are using the same tools for project management and stuff, but you now have AI models integrated with them, right? So they're making you more efficient. They're not taking away your job. They're making you more efficient. That's how you're controlling your financial risk as well as operational risk. Let's look at some of these aspects, right? One of the places where you can use AI is for predictive analytics. Right? For basically, if I have a new project, I want to understand the risk profile of it, financial risk as well as operational risk. If I have all the past accident incident data, if I have all the project information from past projects, right? Geography, where it was located, what were the constraints, what was the cost, everything. You feed everything to it. It learns, again, the same like what I talked about, stock market. It learns all of these interdependencies between those parameters that control your financial risk as well as operational risk. And for a new project, if I feed the same set of 25 parameters, it will tell me what is the financial risk as well as the operational risk I'm going to assume. And based on that, you're going to make a decision whether I want to take up this job or not. If I want to take up a job, what is the cost of demolishing that project is going to be, right? You'll get all of this ready-made information. Real-time safety management, that is big time, right? In most of the job sites, you have cameras. Now, all you have to do is feed the camera real-time to all of these AI models. Imagine a site that spans like about 50 acres or even 10, 20 acres. One site safety manager cannot be going around in circles looking at, is everybody following the OSHA regulations, everybody working a PPE, are there any violations occurring? But these cameras, as I said, a computer does not have a bad day. All I need to provide is that infrastructure. It will, in real time, it will send a notification to the site safety manager on his phone that this person at this particular location is violating this, or there is some other thing that's going to happen, right? That is, I'll show a video generated by a company called DeepX that's already there, and construction industries are already adopting it. Digital twins. Digital twins is something like create a digital asset of an existing plant. And any aspects or operational aspects of that control the risk is actually built into that digital model using science and engineering. And now as I'm deconstructing that model, all of that real-time data is fed to the digital model. And imagine, for argument's sake here, I'm doing some deconstruction, right? And in this digital model, I build all my engineering principles into it, the principles that govern structural integrity. Now, by end of today's work, I have done some work, and that real-time data has come into my digital model. And now that digital model is running all the analysis that control the structural instability. And it suspects that there is a possibility of a collapse here. There is some structural integrity has been compromised because those engineering analyses have been into the digital model. So it calls it a digital twin. And it proactively basically reminds you that there is this going to happen, you better take care of it. And this is, digital twins is big in aerospace industry, automotive industry, in manufacturing, in a lot of where they use it effectively is in managing operations, right? Everywhere there's data churned in any kind of operation, be it oil and gas, anything. That data you have to just feed it to a digital twin and then put all those risk models that are taking those digital twin data, right? Through Internet of Things, you get all of this data and it activates in real time. Compliance management. Give it all the regs, all the codes and everything. It will tell you whether you are complying to everything. Give it all the emails and this one. It is following, it will track all your emails. It says through your emails, it will read everything, what you're writing, texting, everything. Are you violating any compliance, any codes, violations? Because it can read, right? Somebody's saying, hey, we should do this. But if that is in violation with the code compliance, that person may not know. But you have given it the entire Bible of codes, regulations, and standards, so it will know, right? Data-driven decision making. Most effective is for project managers. Again, not taking your job. You can just integrate that into your project management tools, and it will make you take timely decisions, control your cost, get the job done on time. And it will identify where is there downtime. What is that operation that is basically hindering your process? Because it is learned from, what I said is predictive analytics. It's learned from all the past 25, 30 projects that you have done, right? So here's a video that you want to take a look at. This is, again, by DeepX. We have something similar that we developed back when I was talking about AI in 2018, but we use it purely for detecting, like we do a lot of facade inspections, right? So we put these models on drones, they detect in real time concrete spalling, rebar, exposure. But this one is purely for managing or for real-time safety management, right? So let's take a look at this. It can identify any kind of safety violations in real time. You can track people, their position. If somebody's not supposed to be in the area that he's, then you can track that. You can track what kind of operations is working on. Again, real time. Anything that is red, there is a safety violation there. Like most of them, our safety vest is unzipped. So the technology is here. It's already been in adoption. Let's now look into sustainability, right? That's the third part of this talk. We all know the linear economy, right? This is the linear economy that we've been doing it for ever since mankind has existed. We produce raw materials, we process them, we produce building materials. With the building materials, we build buildings, industries, pretty much anything, everything. At the end of the life cycle, we dismantle them and we send it to landfills. And there it's sitting until it's forever if it doesn't decay and decompose, right? And this linear economy has basically contributed worldwide 40% of the global greenhouse gas emissions. About estimated 1/3 of this, when they reach the end of the life cycle, goes to global waste, right? And we are only using 7% of that back in recycling, right? Things have changed, and things are changing because first is I'll touch upon that when I come to the circular economy, right? The alternative is circular economy, right? Because we are all becoming conscious about the world, right? We want to basically make this world more sustainable. Even leave about Gen X, if you look at millennials, Gen Z, they become they want to live in a world that is sustainable. Now, they drive the future. If that is the world they want to live in, we do not have a choice. If the current generation wants to basically use materials that are made out of recycled materials, that is what the market trend or the market driver. Do we have a choice on that? Absolutely not, right? The same, then the other aspect that is basically pushing for circular economy is the technology and innovation, right? Wherein you have all of this technology that can basically integrate for effective recycling, resalvaging, reuse, right? They're also using technology, as I said, in structural design as to how to build buildings that where easily and effectively we can dismantle them. Back, all the power plants or all of the demolition that we're doing right now that were built 40, 50, 70 years ago, there were no principles of resilience and sustainability built into structural design engineering principles. We built all of, like Samis power plant, we kept on building it to serve its intended purpose of producing power. We never thought of how complex it is going to be when you got to tear it down. You should go ask Brian as well as Nick. They often get nightmares about the job, right? So that's changing. The second is regulatory framework. Now, that regulatory framework is purely by the world we live in. If the current generation wants to live in a world that they are conscious about it, they are going to push for regulations. As Jose was talking about yesterday, right? There are 3 ways of dealing with regulations. I'm for the latter because there are 2 things or 3 things that are certain in life. One is death, second is taxes. Now add regulations to it, or you can add whatever you want, right? The regulations are always going to be there in one shape or the form, right? How are you going to adapt to it? So these 3 things are kind of driving the circular economy. And circular economy is what I said is nothing goes to waste. You're going to recycle, repurpose, again build, right? Now, this is just a snapshot of all the regulations that are purely pertaining to sustainability, not decarbonization, not anything. And you can see it's heavily concentrated on the East Coast and the West Coast, again, for the demographics, right? But this is going to change. It is going to, you can see this, all of this is going to be, over the next few years, it's going to be across the landscape of the US, and across the pond, the same thing is happening. The regulations are coming, they're going to hear, and they're going to be staying. Yeah. So how do we now integrate AI into kind of sustainability? We talked about circular design. How do you optimize designs for easy dismantling, right? Energy efficiency. You can have AI models that are continuously looking at your past energy consumption on projects and in real time monitoring it and identifying pitfalls in energy consumption. Scrap and commodities estimation, I'm going to touch upon it, wherein the technology that we are developing, that kind of helps us to maximize recycling and usage of materials. Hazardous materials waste management, right? There are computer vision models that can identify presence of lead, asbestos, and pretty much everything, and these models can be deployed on robots and sent into areas where it is hazardous for people to go. So this is a technology that I want to talk about and how it kind of addresses pretty much everything. We call it as TT SAVE. TT is Thornton Tomasetti. SAVE is Scrap Assessment and Value Estimator, right? So as I said, I've been on projects where we're working with utility companies, and I've been on interviews where I see the bids come in, right? And there's one particular case where the project, the lowest bid was $28.5 million, the highest bid was $55 million. There was another bid that came in at $74 million, but they didn't even make it to the finalists. When I looked into the bid, the biggest thing was the value of the scrap that they estimated. And if you get that wrong, that is basically a financial risk management, because based on that, how much of a money you're going to make by selling the scrap, you're going to appropriately choose what is the margin of profit that you're going to get on this job. And that kind of ties into your operational risk management, right? Because based on what is the value of scrap I'm generating, what is the profit margins I want this, based on that I'm going to choose means and methods that I think is appropriate. Now, if I'm going to make less money, I'm going to choose means and methods that has high risk. So the accuracy matters because it governs both financial risk as well as operational risk. I'll touch upon demo planning as to how we will integrate, or we have seen that in the previous case where we generate all of these digital assets and use that for demolition planning, right? On the other side of sustainability, the same tool, right? Since you have a digital model, you can deploy models now not for scrap assessment, but for hazardous material waste detection. It's the same, this one, but deploy a different model with a different purpose. Intelligent material tracking and sorting, scrap estimation, volume estimations, and we have a demo video that I'll show, and it all kind of ties into optimized waste management. So this tool kind of touches upon, not necessarily addresses everything, but touches upon demolition planning, managing your risk, as well as promoting sustainability. A quick snapshot of how does this work, right? We perform scans. We create a digital asset using drone photogrammetry, using LiDAR scans. Then we create a point cloud model. We deploy the AI models on this point cloud model where the AI model is trained to identify materials. And then once you identify different kind of materials, then there's another layer of algorithms that you deploy that calculate volume and weight, and then they check with the commodity market and give you in real time what is the value. So this is how it works, right? First is you do a laser scan. And here what we're showcasing is a pilot project where we did it on a warehouse. It's a simple warehouse that has some columns, beams, and roofs and trusses, not a lot of equipment, right? So that's the point cloud model that we generated using our in-house Faro focus scanner. And what also the laser scanner does is, okay, I'm almost done. It creates 3D photographs, right? And next, what you got to do is, I'm gonna just quickly show this framework. So the current algorithms that you have for computer vision, they cannot be deployed in 3D space. That's an active area of research. Right now, everything needs to be in 2D. Even for computer visions, it is 2D. So there is a way through which algorithms, we take the 3D point cloud spherical model, photographs, and convert them to 2D. And it's the same, the next step is same like what we did for the cat, right? Pick a architecture, train it, and then in this case, we are training it only to identify columns, purely for columns. And now, once it's trained, it's deployed. So what you see there to the true mask is something, we fed a photograph that you had never seen, and we know where those columns are. And the AI model exactly identified. The predicted mask is what it identified. And you see, it exactly identified the columns that were there in that photograph, right? Because we trained it using photographs previously. And now, we do another layer of algorithms that do the volume and weight. And pretty much, here is a quick 30-second demo of where we screen recorded the demo and presenting it. This is how it looks. It is, again, at a very low technology readiness level. We upload the point cloud model. Give it like 5 seconds, it's gonna, but this is all a screen capture. Yeah, we couldn't speed it up because this was like a real-time screen capture. So that's the point cloud model that got uploaded from the laser scan. Right? You can see all those columns pretty much and beams and anything. Purely now we are training it only to identify structural columns. Right? The next, what I told is you're converting those 3D photographs into 2D. And it'll show some sample photographs of those 2D, right? All of the columns. So next is the trained model is already embedded into the software, into this GUI, right? So it's already trained to identify columns. So you feed all of those photographs, and from those photographs, it's identifying where those columns are. And that's identified. Now, you map it back to the 3D space because all of the volume and the weight estimation has to be done in 3D space. Identifying the objects is done in 2D space, but volume and weight has to go back into 3D space. Again, you project back these identified columns into 3D space. That's what it did, and then you do volume and weight estimations in 3D space. And that's what it identified, all those columns in 3D space in that warehouse. And what it does, it basically looks at all the shapes. Then there's the AIC steel manual. Based on that, it gets the flange width, thickness, and pretty much everything, calculates the volume, then you can connect it to any commodity market and get your report, right? So, but this is, again, only now it's trained for purely for this one, but you can keep, again, as I said, more data, expand it to identifying commodities, to everything. So this is a very low technology readiness level, but that's where we are right now. I think that's pretty much it. I think I've overrun my time by about 5 minutes.